Hey students, we're going to talk about the Pythagorean theorem today. So whenever you hear about that, you might think, okay, we're just going to talk about triangles, but we are actually going to start off by talking about squares and square roots. So I've drawn the most basic squares we can think of. When you were really young, you may have been playing in the yard with some stones. You could have made squares out of rocks. So the most basic square you can make was just find a square stone. So this has 1 stone by 1 stone. This has an area of just 1. You can make a 2 by 2 square. So this would be 2 by 2. This takes up 4 stones. Have a 3 by 3 grid of stones. 3 by 3. How many stones does that take? 9. Make a 4 by 4 stone grid. 4 by 4. This is 16 stones. Or 5 by 5. And this would take 25 stones. So when we get a little bit older, we learn that instead of using physical objects to make squares, we can use measurements to make squares. If we use measurements, it becomes a little bit more clear. So I could have a measurement, a length A on one side and a length A on another. And if this is a right angle, the area of this is A squared. I can go the other way. I could start with an area, and then I say, if I have an area, what is the length of one side of this square? And we could say that is the square root. We could also say 5 is the square root of 25. 4 is the square root of 16. And every number, every real number has a square root if it's a positive number. That means even something that is not a perfect square, so we can pick 17 is very obviously not a perfect square. If I had an area of 17 units squared, I could still have some square where my area is 17 units squared. Thank you. My area is 17 units squared, and what would the side length? Side length would be square root of 17, and that's not a perfect square. It's going to be slightly above 4. As we know, the square root of 16 is 4, so it's going to be slightly above 4. We can know the side length. Square root of 17 is a real number. Okay, in your head, find the side length of each of these squares. 49 units squared, what's the side length there? Of course, it's 7. 100 units squared, what's the side length here? 10 units. 256, this is a harder one. If you are really into computers, you're going to know this immediately. 256 units squared is 16. 16 squared. Okay, let's get to explaining how all these squares relate to triangles. And we relate squares and triangles through this thing called the Pythagorean theorem. We'll lay it out in words and then we'll explain it. In any right triangle with legs of length A and B and a hypotenuse of length C, A squared plus B squared is equal to C squared. We can see that here. We've got A, B, and C. If I square each of these, A squared plus B squared is equal to C squared. This is rather conceptual, so let's try and get it into a picture so you can view what's happening. This is an alternative statement. In any right triangle, the sum of the areas of the right squares on its legs, what are the squares on its legs? This is that square. This is on leg A. The square on leg B is this yellow square. On its legs equals the area of the square on its hypotenuse. So if I add up this green area, green square, I'm going to add that to the area, that should be yellow, the area of the yellow square. Then this should equal the area of the pink square. It's red, I guess. Okay, let's prove this. So we have our given statement which says a right triangle with legs A and B and hypotenuse C. We want to prove that a squared plus b squared is equal to c squared. You might say, well, I don't really believe you, so let's try and make a proof. So the first thing I've done is I've drawn 4 congruent triangles with hypotenuse of length C and legs of length A and B. And I've arranged them such that they form what we're going to call the big square. We could say this is a big green square with a pink square on top of it. Or we could say purple. The area of the purple square can be found in 2 ways. So the area of the purple square, this is going to be c squared, and we're going to find it in 2 ways. So the first way is, because the purple square each has each side of length c. This should, if you can't see it, this is the c, 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 and c. This is a square. This has an area of c squared. This is our area. We can also find our area in another way. So the second way we're going to do it, kind of from one of our problems earlier today, if you were in standard geometry, is that I can take the area of the purple square by taking the area of the larger square and then subtracting away the area of each of these 4 congruent triangles. So we can draw that here. The area of the purple square, let's make sure I'm in purple. The area of the purple square minus is equal to the area of the big square, we'll do that in blue, minus the area of the 4 green triangles. The area of the purple square, we know that's going to be c squared, and that's what we wrote down here. We're going to see if we can get an equivalent statement, or we know that we're going to get an equivalent statement by following this pattern, the area of the big square minus the area of the 4 green triangles. Well, let's look back up. Let's see, what is the length of one of these sides of the big square? We can call that a plus b. It's going to be a plus b. So the area of the big square is a plus b quantity squared. And then I'm going to subtract that area of 4 green triangles. It's going to be 4 times, it's 4 triangles, times the area of each triangle, which is 1/2 the base times the height, AB. So then I FOIL this out, a squared plus 2ab plus b squared. And then when I simplify this, I have 2ab, a squared plus 2ab plus b squared minus 2ab. 2ab's cancel each other. They subtract each other away. And I get c squared is equal to a squared plus b squared. This is the Pythagorean theorem. It's not the converse. Okay, we're going to do some practice. I'm going to do that in another video.